Section 10.6 and 10.8, well, 10.6 deals with secants and tangents, and 10.8 is all about the standard equation for circles. So make sure you get this into your table of contents, and we'll begin with the 10.6 section on secants, tangents, and angle measures. So basically we have three theorems about the intersections of secants and tangents and the angles that they create. The first theorem deals with secants that intersect inside a circle. Now, we've already talked about central angles and inscribed angles, and now we're talking about angles that are neither central nor inscribed. They're just kind of off-road a little bit. So that's one example. We also have an example where the secant and a tangent intersect on a circle. And finally, where the secants or tangents intersect outside of the circle. So here we have two examples. We have one example with two secants, another example with a secant and a tangent line. Okay, so the theorems. The theorems talk about the intersection of those two lines and the angles that they form relative to the measures of the arcs that are intercepted. So if I consider that angle, call it x, and then x has, essentially it cuts off two angles, or pardon me, two arcs. There's arc A, and then out back you see arc B, which is kind of like the vertical angle arc. Now this theorem states that angle x is equal to the sum of half the measure of those intercepted arcs. And so if we pretend that, let's say, A was 80 and B was 40, that would mean x is 60 degrees. So once again, when they intersect on inside the circle, you add together the two intercepted arcs, divide by 2. Now when they intersect on the circle, that angle, it's a little bit kind of strange to see, but if we call that angle x, and the arc that is in the interior of that angle, let's call that arc C, angle x is half the measure of that arc. And so if that arc were 220 degrees in measure, that means angle x is 110 degrees. And then finally, let's take a look at the intersection outside of a circle. Here we create this, this acute angle, and likewise down here we have this acute angle. Again, look at the arcs that are on the interior of that angle. We've got a big arc and a little arc. And likewise down here we have a big arc all the way to the point of tangency, and then that point of tangency splits up into a big arc and a little arc. Now when that red angle occurs outside the circle, you'll find the angle's measure by taking 1/2 times big arc minus little arc. And so for example, if we had 140 degrees and 70 degrees, that means angle x here would be 35 degrees. So to recap, when the two secants intersect inside the circle, you're going to add up the two intercepted arcs and divide by 2, right? It's half the sum. When they intersect on the circle, then the angle is just strictly half the intercepted arc. And when they intersect outside the circle, you're taking half of the positive difference between the two arcs that are intercepted, right? Big arc minus little arc divided by 2. Next, we're going to move to 10.8, and 10.8 is all about the equations of circles. So the standard equation of a circle, just like we have the standard form of a line, the standard equation of a circle is x minus h squared plus y minus k squared is equal to r squared. Note that r represents the radius of the circle, and hk represents the coordinates of the center point. And so, for example, if we had a circle centered at 3, -2, with a radius of 4, we would say its equation is x minus 3 squared plus y plus 2 squared is equal to 16. In other words, 4 squared. And that's it. There's nothing to solve, there's nothing to simplify or to factor. That is it. That is the standard equation of that circle. So let's do some examples here. Let's say we have a circle with a radius of 6 and a center point of -2, 8. Well, based on this formula, based on this equation, the standard form, I know the radius is 6, so that's r, and h and k are -2 and 8, respectively. And so then all you have to do is just sub in those values into this formula. Right? We know x plus 2 squared plus y minus 8 squared is equal to 36. Let's take a look at another example. Here, let's say the center is at the origin. In other words, it's at 0, 0. And we know the circle goes through the point 1, 2. And now, so we need to find the radius. Well, that's quite easily done. We can find the radius using the distance formula, right, between the center point and that point that the circle goes through. And so we have a radius of √5, and we sub in the information we know. The center is at 0, 0, and the radius is √5. And this equation simplifies down to just x squared plus y squared equals 5. For another example, let's say the circle has a center at 3, -2, and then we learn that the circle is tangent to the x-axis. Remember, tangent means the circle touches the x-axis in only one point. And so this problem might seem difficult, but it's actually pretty straightforward. We know the center is at 3, -2, and essentially the fact that it's tangent to the x-axis means we know the radius. Right? There are 2 grid points between our center, 3, -2. So 2 grid points between the center and that point of tangency. And so therefore the radius is 2, and we can sub in our information into the standard form, standard equation of a circle. We'll do one last example, and it's kind of a doozy, so get ready. Let's say the diameter of the circle contains points -2, 5, and 4, 7. So of course, you'll want to graph this to see kind of what's going on. And we know that these points form the diameter of our circle. And so we'll need to find the center point. Well, in this case, the center point is just the midpoint of the diameter. And if you remember your midpoint formula, that means the center point is at 1, 6. Then to find the radius, we can just use the distance from the center point to either one of those two endpoints. I'll pick 4, 7 because all the numbers are positive, so we get a radius of radius of square root of 10, and so therefore our circle's equation is x minus 1 squared plus y minus 6 squared equals 10.